Okay, starting with number 7, the difference with number 7 versus number 8. In number 7, based on order of operations, you're going to raise the 2 to the power of 4 and then apply the negative. So you're going to evaluate the exponent first in PEMDAS before you would multiply by -1. So in this particular case, 2 to the 4th power is 16. You apply the negative and your answer is -16. The difference in number 8 is you're taking a -2 to the 4th power. So that's -2 times -2 times -2 times -2. That's 4. That's 4. And 4 times 4 gives you +16 versus -16. So there is a difference when the negative is sitting in front of the 2 to the 4th power versus you're taking a -2 to the 4th power. Our next one is going to be number 10, and I've tried to on this sheet indicate to you next to the problem if any of the properties on your sheet apply so you can see what I'm doing. In number 10, I'm going to start by first raising everything in this parentheses, which is all a product, all being multiplied, to the 2nd power. Once I do that, I'll multiply it by the 8/9 x y to the 4th. So if I take this 2 and I distribute, and that would be using this property right here, ab to the m equals a to the m, b to the m, what we end up getting, -3/4 squared is 9/16. If I take x squared squared, x squared squared means x squared times x squared, which is x to the 4th. The property over here says when you take a power to a power, you multiply, but you want to understand why you're doing that. Then if I have y to the 3rd times y squared, that's essentially y to the 3rd times y to the 3rd, and I have 6y's. And then I'm just going to rewrite 8/9 x y to the 4th. So now, as I start multiplying, when I take 9/16 times 8/9, the 9's are going to cancel. 8 is going to go into itself once. It's going to go into 16 twice. So I have 1/2. If I have 4 x's over here, and I have 1 x over here, I have x to the 5th. And if I have 6 y's and 4 y's, I have y to the 10th. So my simplified form would be 1/2 x to the 5th, y to the 10th. You could also write that as x to the 5th, y to the 10th, all over 2, whatever feels better. In the last example on this first page, and also seeing which properties we're going to be using, we're going to go ahead and divide. So when we divide the numbers, 48 divided by 12 is 4. Okay? Then I think to myself, if I have 8 A's on top and I have 11 A's on the bottom, the 8 A's on top are going to cancel with 8 A's on the bottom because A divided by A is 1. That's going to leave me with 3 A's on the bottom. If I use this property that says when I divide and my bases are the same, namely the A's, I go ahead and subtract the powers, that would look like 4, and then A to the 8 minus 11 would equal A to the -3. So either one of these answers would be totally fine. This right here, 4a to the -3rd is equal to 4 over a to the 3rd, indicates that when you have a base to a negative power, if it's on the top, you flip it to the bottom of the fraction, make it positive. Had it been on the bottom, you'd flip it to the top and make it positive. So that's what negative exponents do, very much like in scientific notation. In example number 17, based on this property, that if I take a base to the 0 power it equals 1, then I know that this becomes 1 over x to the 0 power is 1, y to the 0 power is 1, so in the end it simplifies to 1/2. Then on number 20, there's a lot going on in number 20, and there's a lot of ways to go about manipulating this. One of the things I'm going to do, and there's a lot of ways to approach this, tons of properties that are being used, but I'm going to get rid of this negative exponent. And the way I'm going to get rid of it is I'm going to move it to the bottom. If it's on the top and it's negative, I'm going to move it to the bottom, make it positive. So here's what this is going to look like. My 5 is going to stay up top. My y squared is going to stay up top. But then on the bottom, I'm going to move this down here and make it x to the third. I now have an x to the third and an x to the fifth on the bottom, which gives me an x to the eighth. And I have my y. I'm going to leave that there for just a minute. That's a times. And in this particular problem, since this whole expression right here is to the negative 2 power, I'm going to go ahead and move it to the bottom, and then I'm going to raise it to the positive 2 power. When this moves to the bottom, there's a 1 still on top. So here's what that would look like. I would say 1 over 2xy cubed squared becomes a positive second power when it's moved to the bottom because it was negative in the top, and then I still have xy. And then I'm going to take my steps to further simplify. So when I come over here, what I notice to myself is that the 5 and the x to the eighth aren't going to simplify. But if I have y squared on top and a y to the first essentially on the bottom, here's what that's going to look like. It's going to become 5y over x to the eighth times 1 over, I'm going to go ahead and we're going to distribute this squared, and that's using this property over here. And what that's going to look like is 2 squared is 4, x to the second is x squared, and y cubed squared is y to the sixth. And then I still have times xy. I'm going to continue simplifying. This becomes 5y over x to the eighth. I didn't do anything different there. Now if I simplify this and clean up the bottom, I have 4. If I have an x squared and an x, I have x to the third, and a y to the sixth and a y becomes y to the seventh. I'm going to keep simplifying. So we're going to scoot this up a little bit. And now what's going to happen is I notice that if I have y to the first up top, I can cross cancel. This is going to cancel. That y is going to go away, and this is going to become y to the sixth. I think that's all the canceling I can do. So 5 times 1 is 5 in the numerator, all over 4. I tend to write those numbers first. If I have 8 x's and 3 x's, I have 11 x's and y to the sixth, and that will be the most simplified form of that particular problem. On problem 1b, I'm going to look at this property that says, essentially, if I have the nth root of a quotient of two values being divided, I can separate that into the nth root of the numerator divided by the nth root of the denominator. When I first look at this problem, I look to see if 27/8 simplifies, but it doesn't. So I think of what we can do next. I'm going to split this up into the cube root of 27 over the cube root of 8. Well, the cube root of 27 is 3, because 3 times 3 times 3 is 27, and the cube root of 8 is 2. And so I can simplify this problem to be 3/2. Okay? In this next problem, you probably saw this back in Algebra 1 or even back in geometry. There's a lot of ways to approach this. I can start the problem and I can distribute. One of the things I notice is I would really like to add these two radicals together, but what's underneath the radical, the radicand, is not the same. But I notice that 27 is 9 times 3, so I'm actually going to simplify that first so that I can add these two radicals before I distribute. But you could easily have distributed to begin with. So here's what I would do. I'm going to break this up into 9 times 3. So what this would look like is the 4 root 3 is going to be on the outside. But on the inside, the square root of 27 is equivalent to 3 times the square root of 3. And then this would stay 4 square root of 3. So now I can go ahead and add what's inside the parentheses to get 7 square roots of 3. Now when I multiply these, 4 times 7 is 28. Square root of 3 times square root of 3 is square root of 9, which is 3. And if I take 30 times 3, that's 90. Take away 6 should be 84 with some mental math there. You can check my work on that. But, and there's a lot of ways to get there. Okay? Then, the next one, which is 1i, this is a brand new problem most likely. This is called, when I have 9 to the 3/2 power, this 3/2 is called a rational or fractional exponent. And rational or fractional exponents can also be written as radicals. So these properties are really important as well. Here's the deal on these. The top number, the 3, is your power, and the bottom number, the 2, is your index. And so what's going to happen here is if I take 9 to the 3/2 and I write that as a radical, the 9 goes under here, and then the 2 is the root. So it's a square root that goes here. And typically with square roots, we don't write the index in there unless it's above a square root. And the 3 is a power, and that's going to go here. So it's the square root of 9 cubed. So I have to think to myself, and essentially what we just used is we used this bottom property here. I'm going to use this top property because I think to myself, is it more efficient to take 9 to the 3rd power and then square root it? Or is it more efficient to take the square root of 9 and then cube it? And so right now I'm showing you this property. It makes no difference if the power or the root is evaluated first. What's nice about this is that now the square root of 9 is 3, so I've dealt with the root, and now 3 to the 3rd power winds us up at 27. So again, it doesn't matter if you evaluate the root or the power first, whatever's more efficient for you to evaluate first. For 1k, we're going to continue with our knowledge of negative exponents. So for example, if I had 5 to the negative 2, that would equal 1 over 5 squared. If I had 1 over 5 to the negative 2, that would equal 5 squared. So to get rid of the negative exponent, if your value's in the numerator, it goes to the denominator and the exponent becomes positive. And likewise, if you have an exponent that's negative in the denominator, it moves to the top and the exponent becomes positive. So let's see how that applies to this problem. In this problem, 4/9 to the negative 3/2 power, the first thing I'm going to do is apply the negative exponent, and that has the effect of flipping our fraction. So the first thing I would do is make it 9/4 to the positive 3/2 power. 9/4 doesn't simplify, so I'm going to use this property right here to go ahead and to raise that power to the numerator and the denominator. So that's going to be 9 to the 3/2 power over 4 to the 3/2 power. And then I'm kind of stuck again. So I think to myself, well, those are rational or fractional exponents. I can change those to radicals, and maybe I'll be able to evaluate that. So that would be the square root of 9 cubed over the square root of 4 cubed. Now I could have written that as the square root of 9 and put the third, the power of 3 right here. But from the previous example, I know that 9 and 4 are perfect squares, so I'm going to square root those first and then I'm going to cube them. So then if I proceed, this would equal 3 to the 3rd and 2 to the 3rd, which ends me up with 27 over 8 as my final answer. Again, lots of ways to get there. Okay, moving on to 4b. Simplify the square root of 60xy cubed. You did this last year in geometry and probably the year before in algebra with numbers, maybe not with variables. So let's approach the number first. When I look at 60, I think to myself, you can break it up however you want, but I try and find the largest perfect square. So I know 60 is 4 times 15. There's only one x, and for the y's, I can break that up into y squared times y. So we're looking at square roots, we're looking at perfect squares. So the square root of 4 is 2. So a 2 comes out, that's what the square root of 4 is. 15 is not a perfect square, and there's no perfect squares hiding under it. And then y squared, the square root of that, is y. So I have 2y on the outside. On the inside, I have 15. I still have my x, and I still have this y. So that is the simplified form of square root of 60xy cubed. To check this, you could also take this 2y, you could square it to get 4y squared. That puts it back underneath, and if it multiplies to 15xy to get this, you know you're in business and you've done it correctly. Okay, looking at 4i, when I look at this, there's nothing I can simplify to begin. Square root of 2 doesn't simplify, square root of 6 doesn't simplify. So when I'm multiplying, I'm going to multiply the outside by the outside, that gives me 8, and the inside by the inside, that gives me 12. But as mathematicians, we're always looking to simplify. So I know 12 is made up of 4 times 3. Well, 4 is a perfect square. So what I'm going to do is, the square root of 4 is 2. There's already an 8 out there. So when I take the square root of 4, I bring out a 2. Whatever gets brought out gets multiplied by whatever's already out there. And then what's left under the radical, poor little 3, not a perfect square, that stays underneath. And so my final answer would be 16 times the square root of 3. Finally, on this page, for this last one, we're going to scoot this up just a little bit. Okay, for 4k, now these are fourth roots, so I'm looking for values that multiply by themselves 4 times, create perfect fourth powers. So here's what we're going to do. I'm going to go ahead and multiply first. So I'm going to get the fourth root of 4 times 8 is 32. X cubed times x squared, that gives me x to the 5th. Extend my radical, and then I have a v to the 5th. Okay? So I'm going to break this up. I'm going to think to myself, I know that 16 is 2 times itself 4 times. So when I break up 32, I'm going to do it by 16 and 2. For x to the 5th, I know that's equivalent to x to the 4th times x, and v to the 5th is v to the 4th times v. Because I know that the nth root of a to the nth power equals a. So if my index matches my power, they cancel. Well, that's what I'm trying to do here. What I'm trying to do here is my index, if it matches my power, they cancel each other. Well, the fourth root of 16 is 2. Okay? The fourth root of x to the 4th is x. The fourth root of v to the 4th is v. So that's what comes out. It's still the fourth root. So this is 2xv times the fourth root of. There's a 2 left underneath. There's an x left underneath. And there's a v left underneath. And so what we're doing in this unit is we're extending past square roots, but the process is the same no matter if it's a square root or a fourth root or a fifth root or a third root. On this last screen, I'm going to use a property similar to what we've seen before, and that is if I have the square root of a quotient, or I'm sorry, an nth root of a quotient, and that doesn't simplify, I can break it up into the nth root of the numerator over the nth root of the denominator. So I look first at the square root of 36x to the 4th over y squared, and nothing simplifies. So to see if I can simplify it, I'm going to break it up into the square root of 36x to the 4th over the square root of y squared. Well, the square root of 36 is 6. The square root of x to the 4th is x squared, because x squared times itself is x to the 4th. And then the square root of y squared, again, this idea that the index here is 2, and when the index and the power match, they cancel out, and we know the square root of y squared is y. So your answer, most simplified, is 6x squared over y. All right, in 4.0, we've again seen this in prior examples today and last year. The way it looks right now is that it doesn't look like you can add anything. because the radicand of 6 would have to match the 24, would have to match the 150. But before we decide that we can't do it, we need to see if we can simplify. So 6 doesn't simplify, but 24, I can break that up into 4 and 6. And if I think money, because quarters 25 is a perfect square, I can break this up into 25 and 6. So as I go through and simplify, 5 square root of 6 stays 5 square root of 6. There's already a 3 out there. The square root of 4 is 2. So when I bring a 2 out, it's going to get multiplied by the 3. But there's still a 6 left underneath. And here, the square root of 25 is 5. There was nothing already out there, so it's just 5. And then the 6 stays underneath. So we get 5 square root of 6 minus 6 square root of 6 plus 5 square root of 6. And if we simplify 5, now what's nice about this is that you have like terms. All these radicands are the same, which is what you need when you add and subtract radicals, not multiply and divide. But 5 take away 6 is -1, and -1 plus 5 would wind us up with an answer of 4 square root of 6 as your final answer. All right, in number 5A and B, these last two examples, 5A should be pretty similar. Rationalizing the denominator is essentially getting rid of the radical from the denominator. And last year, the way that we did this is the way to get rid of a square root of 5 is to multiply it by itself. In essence, you're multiplying by 1 because square root of 5 over square root of 5 cancels, that's 1. But what's going to happen now is that on the top you get 2 square root of 5, and on the bottom square root of 5 times square root of 5 is square root of 25, which is 5. And you've rationalized the denominator. Interestingly enough, 2 over square root of 5 and 2 square root of 5 over 5 are totally equivalent. The only difference is this one has a radical in the denominator and this one does not. But if you plugged them into your calculator and you saw, you would see that they're totally equivalent. Okay, D is a little bit different. If you start messing with D and you try and multiply just by root 2 over root 2, that's not going to get rid of the root 3. If you multiply by root 3 over root 3, that's not going to get rid of the root 2. So we have started talking about conjugates. Conjugates essentially are two binomials where the only difference is one's a plus, one's a minus. Even though square root of 2 plus square root of 3 is not a binomial, it's binomial type, and so what we're going to do here is we're going to multiply it by the conjugate of the denominator, and the conjugate of the denominator would be, instead of square root of 2 plus square root of 3, square root of 2 minus square root of 3. And we're going to do the same to top and bottom, because in essence we're multiplying by 1. Okay? When we do this, I'm going to go ahead on top and I'm going to get 2, and I'm going to leave it for right now. I'm not going to distribute the numerator. We'll see if it cancels in a little bit. And on the bottom, if we FOIL this, first times first gives us 2. Outside gives us negative root 6. Inside gives us positive root 6. And last gives us minus 3. So I'm going to come down here because I'm running out of space. And so if we simplify this, we're going to get 2 times root 2 minus root 3 over, if I come back here, these cancel out, and 2 minus 3 is -1. Typically, we don't like to leave the negative in the denominator, so I'm going to move it up top. And if I do that, the negative would come here. So I could write my answer as this. Or if I did distribute, I would get -2 square root of 2 plus 2 square root of 3. So either one of those answers is totally awesome.